In this lesson, we're going to look at finding the area between two curves by using calculus. I don't know if there's another way you can get the exact area. Anyway, finding area between two curves. So we're just going to start with real problems instead of crazy notes or something. Find the area of the region contained by the following graphs. And here I've given you four graphs: x plus 1, a line, a parabola, and then two vertical lines. And first thing you're going to have to do is visualize the region because you have to determine which function is on top or bottom or left or right. So let's start by graphing this. We have uh, a y-axis and x-axis. And the graphs don't have to be perfect. You just have to have them in correct position with relation to each other. So x plus 1 is a line, a y-intercept of 1, and a slope of 1. So that line is going to look something like this. I'm going to make it a little bit thinner. There we go. Let's go with red. So that line's going to look something like that. That's about what the line y equals x plus 1 will look like. So let me label that. And then we have the parabola y equals 9 minus x squared, which is a parabola opening down, shifted up 9 units. So I know that parabola is going to look something like this. And then we have the lines x equals -1, which is going to actually hit right here. So we have two vertical lines. X equals -1 right here, and x equals 2, um, which I wonder where 2 is going to hit. I'm going to do a little bit of work here. Uh, I'm going to plug in 2 to both my functions because I need to know if x equals 2, is it before this intersection or is it after this intersection? And that's important to know. So there's a couple of ways we could find that, but what I'm going to do is simply plug in 2 to my functions. So if I plug in 2 here, 2 plus 1 is 3. So that's going to be the ordered pair 2, 3. If I plug 2 into this one, 9 minus 2 squared is 5, which would actually be above. So I know that 2 is going to be to the left of that intersection. So there's my vertical line x equals 2. Wow, that is way off the mark. There, x equals 2. Okay, so now I know that I'm looking for the area of this region right here. This is what we're looking at. I can see that my top function is the curve 9 minus x squared. The bottom function is the line. And then I will simply set up my integral, antiderivative. And I'm going from an x-coordinate of -1 to 2 of my top function, 9 minus x squared, minus my bottom function, which is x plus 1, dx. And then we simply work out that integral. One of the biggest mistakes people will make is they'll get silly with their distributing the negatives. So that's -1 to 2, 9 minus x squared, minus x, minus 1. Combine like terms, and that turns into the antiderivative -1 to 2 of 9 minus 1 is 8 minus x squared minus x dx. And now I can do the antiderivative. So the integral of 8, antiderivative of 8 is 8x, minus x squared is x cubed over 3 is the antiderivative, minus antiderivative of x squared over 2, and we'll evaluate from -1 to 2, and plug in. So now once you get to once you get to this very first integral, the rest of it turns into old integration techniques that we've already done. Um, and so really the hard part, the new stuff, is just setting up. So at this point, I've gotten down to the antiderivative. I will plug in 2. So 8 times 2 is 16 minus 2 cubed over 3 minus 2 squared over 2 minus, and make sure you put this in parentheses, 8 times -1 minus -1 cubed is -1 thirds. -1 squared is +1/2. And I'm okay if you leave your answer like this. If it's a multiple choice question on the AP exam or on a test, they will be cleaned up. So don't forget your order of operations and stuff. But there is how we're going to solve the area between two curves. Simply graph it, determine which one's on top and bottom, and then set up the integral top minus bottom. Now let's try a different one. Same directions, new functions. We have 5x minus x squared and y equals x. Again, we have a parabola and a line. So let's graph those two. Y-axis, x-axis. So I'm going to do the easy one first. Y equals x is pretty straightforward. So let me graph that real quick. I'll do it in red. and y equals x is going to come through looking something like that. And here's what I want. And then I need to graph 5x minus x squared. I know it's a parabola that opens down, which makes me, I'm pretty sure it's going to be up above the graph like this. But I'll want my graph to be somewhat accurate. And to do that, I'm going to find the x-intercepts. So I'll set this thing equal to 0. If I factor out an x, you get, what, 5 minus x equals 0, which tells you you have x-intercepts at 0 and 5. So when I graph the parabola, I know it needs to hit the x-axis at 0, and then again over here at 5. And the parabola is going to come up. Oh, that was ugly. And then it's going to bend back down. Then I'm going to hit at 5. And I can see my region where I'm finding area is this region right here. Now the problem we run into with this problem is we have the beginning x-coordinate, but we don't know the second x-coordinate where the region ends. I need to find that x-coordinate. I do know as far as the setup, my top curve is the parabola, 5x minus x squared, minus the bottom curve, which is just x. I know the region begins at an x-coordinate of 0. And the next x-coordinate right here, we're not so sure. So what we need to do is find the intersection of those two graphs, which means we'll set the equations equal to each other. So 5x minus x squared equals x. Move the x over. 4x minus x squared equals 0. Factor out the x. And you get x equals 0 for this factor, which we already knew, 0. And 4 is the one that we weren't aware of. So our region goes from x equals 0 to x equals 4. So pretty common to have to do this to set the equations equal to each other. Find the intersection. Find the intersections of the two curves by setting them equal to each other. And now I have the integral set up. I will combine my like terms. That's 5x minus x squared minus x, which is 4x minus x squared. Integral from 0 to 4. And then we'll do the antiderivative and clean that up. Antiderivative of 4x is 2x squared minus x cubed over 3, evaluated from 0 to 4. Plug in 4, 2 times 4 squared, 16 minus 4 cubed, which is 64 over 3. So I plug in 4, now I plug in 0. 2 times 0 is 0, 0 cubed is 0. Always plug in the 0. A lot of times the 0 just ends up canceling out and not being needed. But every now and then when you plug in 0, you actually do get a numeric answer. So make sure you plug in both limits of integration every time, even if you do have a 0. So again, just like the first problem, we graph it, determine which function is on top and bottom. In this case, we had to find the point of intersection, because that point of intersection was my upper limit of integration. Let's try this one. Now here I've swapped it up some. Notice this is x equals 2y squared, which you could try to solve that for y if you want to. It's going to get really ugly, but what we have here is a parabola that is going to open to the right. It's a parabola that opens to the right, so I'm going to graph that. Now I don't know exactly what it's going to look like, but I know that a parabola that opens to the right, ooh, my axes are way off. I could plug in a few points to make it really accurate, but I know it's going to start at the origin and open to the right. So here's the parabola, y equals, or x equals 2y squared. And since that is a function of y, this is not a normal function. This passes the vertical line test. This is x being a function of y. That makes me think in my head that what we're going to have is a left and right situation here, which means everything's going to be in terms of y. And the reason that's important is because my next equation, x plus y equals 1, I'm going to need to find a way to graph that and think of it in terms of y. Now, normally when I solve that to graph, I'm going to move the x over. We have negative x plus 1, which actually does help in terms of the graph. That's a y-intercept of 1 and a slope of negative 1. So this is going to be a line that drops down like this. So there's slope of negative 1, So there's that line. But what I see here is a right and left situation. So I will do a right curve minus a left curve, and that's what our general setup here. So we have a right curve minus a left curve, but the problem with right minus left is it is a dy integral. It is not a dx integral. So this equation, calling this line y equals negative x plus 1, doesn't help me because it needs to be in terms of y, not in terms of x. So rather than negative x plus 1, we're not going to move the x over. I'm going to move the y over and call this line x equals negative y plus 1. Because if I do that, that gives my function in terms of y. Now I can set up my integral. It's the antiderivative of the right curve, negative y plus 1, minus the left curve, which is 2y squared. This is a dy integral. And now again, we have a problem because I don't know my limits of integration. I need to find my points of intersection right here and right here. So let's set the two equations equal to each other, which my graphs were 2y squared and negative y plus 1. And we will factor and solve that. So let me pause the video and I'll do that real quick. There we go. So I got my points of intersection, and I got y coordinates of negative 1 down here all the way up to positive 1/2 up here. And those are my limits of integration. So negative 1 up to 1/2. Then just for the sake of making this integral aesthetically pleasing, I'm going to drop those parentheses, negative y plus 1 minus 2y squared. And then we will do the antiderivative, plug in the limits of integration, and find the area that way. So I'm actually going to pause the video while I do that antiderivative. At this point, you should be able to do antiderivatives in whatever calculus class you're taking. It's the setup, it's the setting up for the area between the curves that's new. So now that we've set it up, let me pause this and do the antiderivative. Okay, there we go. So I did the antiderivative and plugged in 1/2 and negative 1. I did not simplify it, but you know, this is calculus, not arithmetic, so I'm going to assume that you can clean that up if needed. So I have one more problem. Another two functions of y, so I'm automatically thinking when I see all these functions in terms of y, I'm automatically thinking that my setup's going to be the integral of my left curve, no, my right curve, minus my left curve. It will be a dy problem, which means I need to set everything up in terms of y. And I'm going to start by graphing these, and these are a little bit tougher to graph. This very first one, I see that it's x equals y squared minus some stuff. I know that this one is going to be a parabola opening to the right, because it's a positive y squared. This one is going to be a parabola opening to the left, because it's a negative y squared. And then in order to find out where those graphs are going to hit, I'm going to find the intercepts, except this time we're actually going to find y-intercepts. So for this first equation, if I factor out a y, you get y minus 4, and we have y-intercepts of 0 and 4. The second equation, if I factor out a y, you have 2 minus y, set that equal to 0, and you get y-intercepts of 0 and 2. And so that's going to help me get the graph of these two, or graphs of these two functions. Y-intercepts are 0 and 4 and 0 and 2, so I don't think I need much in the way of negative y, so I'm going to give myself a lot of room above the x-axis. This first graph, I'll do it in green. It's going to open to the right, and I know I have y-intercepts at 0 and 1, 2, 3, 4. So that parabola is going to look something like that. And the red one, x-intercepts or y-intercepts of 0 and 2, so it's going to come up and look something like this. Now looking at this graph, I know that one of my limits of integration is 0, the y-intercept is 0, but this y coordinate intersection, I'm not sure. I'm hoping it's 3 because that would be nice and sexy, but we'll see. We're going to solve that by setting the two equations equal to each other. And so here, let's find the intersection. I know one of the answers I get when I solve this is 0, but it's that other one we're not too sure about. Let's see, so y squared minus 4y equals 2y minus y squared. And then let me solve that real quick. Okay, so I solved that, and I do get a nice clean y-coordinate of 3. So my y-coordinates of intersections are 0 and 3, so my upper limit is 3. And then I got to do the right curve minus the left curve. The right curve was 2y minus y squared, minus left curve, which is y squared minus 4y. And then we will distribute the negative and solve that integral. So integral from 0 to 3 to y minus y squared minus y squared plus 4y dy. Combine like terms. That would be 6y minus 2y squared. And then we'll do our antiderivative. So that would be what? 3y squared minus 2y cubed over 3. Evaluate it from 0 to 3 and plug in. So 3 times 3 squared minus 2 times 3 cubed. And then plug in 0, and I think you get a bunch of zeros. 3 times 0 squared minus 2 times 0 cubed. And there would be your answer for this one. So graph the functions. Find the points of intersection if needed. Always set up top minus bottom or right minus left as far as the position of the functions. And then we'll integrate and evaluate.